Buenos días a todos, buenos días aquí a la gente que está en la sala, a aquellos que están también online, bienvenidos a estos seminarios Torroja. Y hoy pues tenemos un invitado muy especial, es una persona que tiene un investigador con gran renombre, pero además es un gran amigo, ¿vale? He's going to give the talk in English, so let's move into English. As I said, he's a very good friend, okay, for a long time ago. We have been collaborating for already many years. So I'm glad to come here and accept the invitation to come here. So he's Professor Jean-Baptiste Espinosse. He's as I brought here, where is the pointer? Yeah. He's a geological engineer. He has a PhD on physical chemistry that he did in the United States, in University of Wisconsin. He's professor at the Paris School of Physics and Chemistry at ESPCI, Paris. He's director of the Soft Matter Science and Engineering Laboratory of the CNRS. And he has, vast experience and research on different topics that includes areas like catalysis, aqueous surface chemistry of oxides, and he's an expert on NMR, solid state NMR. What he's currently working, again, plenty of research going on. He has very relevant studies on physics and chemistry of organomineral interactions. He also ran studies on research on soft biocolloids. He's applying non-conventional NMR methods. This is where we go and collaborate. And of course, and this is what is related to the talk today, on chemistry of low carbon cements. Welcome, Jean-Baptiste. Thanks again, and thanks to everybody for attending. And afterwards, we will have time for questions, and hopefully, we all participate. Thank you very much.
So thank you, Marta. So in case I forget at the end of the talk, thank you for the invitation. This is very nice to be here. This is the last one, actually. Yeah. Okay. So it's very nice to be here. I think the first time I came here was at the beginning of the century, so it's a long time ago, and so I'm very honored to be here. So Marta already introduced my research activity, but I will spend little time to talk about the institution where I'm working on, because this is relevant to what we are going to discuss together today. So I'm at as Marta said, at the School of Physics and Chemistry, an engineering school devoted to physics and chemistry in Paris, but it is part of a groupment of schools which is called PSL University, PSL standing for Paris Sciences and Letters. And inside the school, I'm part of a lab dealing with soft matter, okay? So just to give you the overall picture, PSL, Paris Science of Letters, is a groupment of schools in the center of Paris. So you may know, for instance, the School of Mines or the School of Chemistry. And our hospital, our medical school is Institut Curie, l'École Normale, and us, the École Supérieure de Physique et de Chimie Industrielle. So industrial is important because we try as much as possible to link fundamental research to industrial subjects. Okay. So you see, so the school is being reconstructed, but we are keeping the old facade. And you see, we are not very old. I mean, the school dates back from the end of the 19th century, 1882 to be exact. So this is very different from other engineering schools, like for instance, the École des Ponts, who was basically an offspring of the Enlightenments, right? So either as the École des Ponts, the Enlightenments during the monarchy, or the offspring of the Enlightenments, which is the French Revolution. So we are much newer than those schools. And this is an interesting point, but again, you will see it relates to the talk and the interlink between physics and chemistry, is that the origin of the school dates back from the Franco-Prussian War, when France lost the eastern part of France, Alsace-Lorraine, and most of its, a large part of its chemical industry, and more importantly, its only chemical engineering school in Mulhouse that became German. And so a lot of people from Alsace moved to Paris with only one thing in their mind, was to gain back their homeland, right? I mean, to get back Alsace to their homeland, which is France. And so they came to Paris, and well, I will make a long story short, but they decided to build the school from scratch. They were chemists, and so at the time there were no more chemistry school in France, because the only school became German. And so they wanted to build the chemistry school in France. But they were smart people, and they realized that the 20th century would be the century also of physics. You know, it was the time of electricity, mechanics being formalized largely following the end of the 18th century. And so they decided not to found a school of chemistry, but a school of chemistry and physics. Okay, and so that's what's important, is that it's the and here, it's not or. Okay, so the students, they study physics and chemistry. They do both at the same time, and I think that's what's very important in terms of their formation and their specificity. So it's really multidisciplinary. Okay, as I said, physics and chemistry, and there is an opening towards biology, so they can at least talk to biologists, if not being biologists themselves. And because this is an engineering school, there is a name industrial in the name, but the idea when it was founded, and that's still alive today, is that innovation is grounded on fundamental research. Okay, so there is also a very strong coloration in terms of fundamental research in the school. Actually, you have recognized here Pierre Curie, which was one of the first professors in the school. And voila, so for instance, 4 elements of the periodic tables were discovered in the school. So of course, polonium and radium with Marie Curie, but also lutetium and actinium. So you see both are at play. So the specificity is multidisciplinary and linking fundamental to research and understanding to usage properties. Voilà. So if we want to cover the whole spectrum, we have a lot of laboratories in the school, and the laboratory I belong to is a soft matter science and engineering laboratory, where we deal with soft matter, which is essentially polymers and colloids. Okay, so meaning systems where energy is very easily dissipated within the bulk, and at the same time, interfacial energy plays a very, very strong role. Okay, so in there you will find, of course, polymeric materials and colloids, but any system actually, including cementitious paste, where you have strong interfacial and dissipation effects. So this is what we are going to discuss today, and we'll see that if you want to understand soft matter, you have really to go across scales. Okay, so you have to go from the chemistry to the molecule to the larger macroscopic properties. So this is what we are trying to do essentially, with mixed successes. So my talk will be sometimes a little confused because things are not always very clear cut, but we are trying to at least understand a few elements in those systems. Okay, so more specifically, the talk today is about Actely activation. So in the broad sense, covering at the same time slag and activated clays, thermally activated clays. So to due credit to the people who actually did the work and most of the thinking behind that, Claire Payard, Alice ex-PhD student, Alice current PhD student, and a postdoc, Quang Hung. So I will again focus on the molecular perspective to see what we can understand in terms of usage properties from the molecule sides, and I will I will divide my talk in 2 parts, but you will see at the end that we can somehow link to each other. So the first one will deal with organic admixture and how the understanding of the physics of the organic admixture in solution can help us understand at least some rheological behavior of the cement paste. And in the second part, I will look more closely at the oxide in itself and try to understand the mechanism, what is hidden between this idea of alkali activation. Okay, so let's start with a general statement. It's very, very fast because you all know that. You know that basically we are lucky when, I mean, the beauty of cement, it is that it's based on calcium chemistry and hence very high reactivity in water because calcium, as you know, is a very hydrolyzable cation, highly hydrolyzable cation. But our source of calcium is limestone, and so we have to decarbonate, and this is what we try to avoid, right? So we are substituting cements, or at least clinker, with other source of silicon and aluminum and eventually calcium, but with less calcium. And as a result, we have powders that are less reactive with respect to water. So we have to activate them, right? So to the formulation, we have to add an activator. Before life was easy, we would have the calcium silicate and the calcium aluminate. We put it in water and it reacts spontaneously with water. Now we are substituting with materials that are sometimes glassy or almost always disordered, but they are not very, I mean, they need to be activated. They don't react very fast with water, and we have to accelerate the reaction, okay? So this we know. This is illustrated in this heat flow rate development over time in an actually activated cement paste, where you compare the Portland cement with just slag in water, and you see that if you put slag in water, there is no chemistry, no heat released due to any dissolution, or very little, and you have to activate to recover the reactivity that you had spontaneously in Portland cement. You also know that we need to control the rheology, and nowadays we know more or less how to control the rheology of ordinary Portland cement with chemical admixtures. And the goal being to, in part, restore the initial fluidity of the paste by controlling grain-to-grain interactions that are blocking, jamming this, I mean, not jamming, but blocking the shearing, I mean, not helping the shearing of the system, let's say, and resulting in a yield stress. And one of the manifestations of those superplasticizers, in addition to the cement paste, is to depress the initial distress by reducing the grain-grain interaction. And as you know, they do it by adsorbing on the clinker grain. This is not to scale at all, this drawing, but they adsorb on the clinker grain, and due to their architecture, their molecular architecture, I will go back on this later, they induce steric repulsion between the grains and they therefore minimize the grain-grain interactions. So in terms of yield stress, excuse me, this is very clear. If you take a suspension of slag in water, you have a yield stress, and if you add superplasticizers to it, you decrease the yield stress. Okay, so those superplasticizers are efficient with respect to slag, just as with clinker. The problem is that we have to combine them with the activation, because the slag in itself is not reacting. And that's when the trouble starts. This is illustrated in this figure here. Again, the shear stress that you observe on a suspension of slag in water. Superplasticizer, you depress the yield stress, and if you add the activators, here sodium hydroxide or sodium carbonate, you see that the efficiency of the superplasticizer is lost. You recover the initial curve as if you had put no superplasticizers in it, right? So clearly they are not compatible, or at least their effects are not compatible. You cannot use the superplasticizer you use in ordinary Portland cement in actually activated materials, in presence of activators. So that's what we are going to try to understand together this morning, or at least have some elements of understanding. So this is a very early time. This is really just no reaction here. Okay, voila. So that's what I said. If I lose the dispersing effect due to the PCE when I have the activators in the solution. If I use another activator, which is sodium silicate, very commonly used in industry, the situation is a little different, so I won't talk about it right now. I reserve that for later on in my talk, because you see that already silicate anions have a dispersing effect, a deaggregation, tend to deaggregate powders. It's very well known in clays, for instance. So the yield stress issue is not as strong when we are dealing with sodium silicate activation. So I will focus on the issue of, for the beginning, hydroxide and carbonate activation. So we simplify the system with respect to a true cement paste. We just use slag, okay? So no cement, no Portland cement. It's not a blend, just pure slag. We activate with hydroxide or carbonate, and we'll see later on what goes on when we also activate with silicates, or we don't activate and we compare the behavior of those systems, okay? In presence of a very common superplasticizer, which is a polymetacrylate backbone grafted by a polyethylene oxide, by a PEG that is methyl terminated. So it's a very commonly used polymer by the industry and sold in relatively high amounts. The beauty of those polymers, as you know, so for the time being, I think I'm just repeating things you already know, is that there is a great diversity of architecture. I mean, with this architecture, sorry, you can have a relatively large types of behavior playing on the length of the polymetacrylate backbone, on the length of the side chain, the density of the side chains, esterification ratio here, and the length of the backbone. So I would just, depending on those parameters, this has been studied by people dealing with polymer physics for like 50 years at least. They have described very well the behavior of those polymers, what they are called comb due to the shape polymers. Here they are copolymers, but it's true also of polymers. Their behavior in solution. And when they are in when they are in a good solvent, the chain deploys. I mean, they prefer to interact with the solvent, water in our case, than with other monomers of the polymers. When they are in bad polymers, they prefer, in bad solvent, the monomers prefer to interact with each other. So the polymer is not in solution anymore. Okay, it doesn't interact with the solvent. And in real life, very often, and in that case, you are in between, you're in what we call a theta solvent. That is the energy of interaction between between one monomer and another, or one monomer of a molecule of solvent of water is about the same. Okay? So if you make the hypothesis that you're in theta solvent, you can work the thermodynamics and take into account the entropy of the chains and draw a phase diagram. So this is, as I said, something that has been described by De Gennes 50 years ago and applied to copolymers like 25 years ago by Gay and Raphael, and you describe a phase diagram depending on the architecture, and you can have different conformation in solution. So those little drawings here describe the conformation of the polymer in solution, and you see that the main unit in terms of the statistical behavior of the chain is what we call a core or a blob or a coil, okay, which it's the basic unit that describe the motion, the overall motion of the chain. And you have different configuration and sizes of those coils, of those blobs. In the original De Gennes paper, they were called blobs. And the ones that are mostly used, most of those that are used by the industry, and the one that I'm going to discuss today as an example, are in such chain length, graft length and grafting ratio that they are in the phase diagram in the area where they form flexible backbone worms. Okay, so they are like a pearl necklace, if you want. Okay, So you should not see those polymers as combs, like I naively drawn them in the previous schemes here. They are actually like a pearl necklace. Okay, so we draw this to have a better understanding, but it doesn't represent the real conformation in solution. In solution, they look more like something like that. Okay, and you have the stochastic motion of those coils along the chains. Okay, so we are in this configuration. So once, okay, so this is just polymer physics, polymer in theta solvent. So now what happens? Does that remain true in presence of activator? And of course, the answer is no, otherwise I wouldn't be here. Okay, but let's pretend there is a suspense. And you remember that we lose the dispersing effect. And what I'm going to, the message I'm going to try to carry today is that part of this has to do to the conformation of the polymer in solution and its dependence on the ions in solutions. So again, no superplasticizers, activation at very early time doesn't change the yield stress of the system, taken as the minimum of this curve here. But what's interesting is that when I add the superplasticizer, do you remember without activation it worked very well? The yield stress was drastically depressed by orders of magnitude. And as I gradually increase the concentration in sodium hydroxide, going up to 3 moles per kilograms, but those are intermediate values, you see that the yield stress comes back progressively. Okay, so we are not dealing with a phase transition here. It's more complex than that. But clearly, the presence of the sodium hydroxides modifies the behavior of the polymer. So let's focus first on the sodium hydroxide because this is where everything is simplest, I think. Okay? So let's go back to how those polymers are working. They adsorb on the solid grain, clinker or slag. Because of their blob conformation, they have a certain geometrical extension in solution, and they therefore induce steric repulsion between the grains. So the first step is adsorption, and the first element is steric repulsion. So why is it not working? Is it because it's not adsorbing? Well, no, it's not. I mean, you can measure by different methods, but here it's by total organic content measurements. By difference, you can measure the amount of polymer that's adsorbed in the solution, and you see that the isotherm with sodium hydroxide or without sodium hydroxide is exactly the same. So the presence of sodium hydroxide dissolved in the water doesn't impact the adsorption on the slag. Okay, so there's some disagreement with that statement in the literature, but here I think it is very clear. Okay. So it's something else. So if it's something else, say, as we say in French, pince-moi avant bateau, okay? So if that guy falls from the boat, there is only this one left, okay? So it has to be linked to some modification of the steric effect of the polymer. So remember, the steric effect is associated to this conformation in solution, okay? So in solution, you have blobs. If absorbed on the surface, Robert Flatt has shown that experimentally doing AFM, the blob model remains correct. You just have an excluded volume due to the presence of the surface, but it doesn't basically change the thermodynamics. You just have a square root of 2 prefactor here. If you want to describe the radius of the blobs adsorbed on the surface with respect to the blobs free in solution. It's just they scale in the same manner. Okay, so scale is really the right word because the size of the core or of the blob, all of this is synonymous, actually scales with, as I said, the graft density, the graft length. But this is really a scaling law, okay? And you have prefactors that depends on the monomer sizes, but also on the solubility of the polymer. The property I mentioned before, that is how much the monomer prefers to interact with water or with another monomer. So this is what we call the Fleury parameter that describes the quality of the solvent. Okay, and it varies between 0 and 1 in the extreme. And so this is for theta solvent, okay? And there is even another prefactor here that is unknown because those are just scaling laws, so we don't have the absolute values. Okay, so that's another point I want to draw your attention. Sometimes in the literature people put an equal, and I might have done it before also, put an equal sign here, but this is not true. It's just a scaling law, okay? But we know, okay, so it scales with the architecture of the polymer. It scales with its nature, what kind of monomers are involved, but it also scales with the solvent quality. And this is what's affected here, okay? We have no direct way to measure the Fleury parameter. It's actually, you can model it, you can calculate it by models, but even the models are very questionable because it's actually very, very difficult to model solvent polymer interaction. Okay, people can model polymers in vacuum, see how they behave, or polymer melts, but in a solvent, it's actually extremely tricky, and there is no numerical simulation so far that are accurate. So we have to resort to measurements. So one measurement that is well known in the literature is to look at the maximum, the temperature of precipitation, TP, okay, for a polymer. So here it's a PEG, which is relevant here because our side chains are PEG. And what you see here is as you increase the salt concentration, the precipitation temperature drops, which means that the quality of the solvent drops. The polymer becomes less and less soluble. So it's still soluble, but it's less happy, let's say. Okay, so it's not a phase separation. It's important. It's not a precipitation. So here is a precipitation temperature, but it's tells us what's going on right before the precipitation. Okay, so you see that it drops with the concentration in salts. So first information. The second very important information that it depends on the anions. You see phosphates are more efficient to, the solvent quality is more efficiently degraded by phosphates than by sulfates, carbonates, or hydroxides. And again, this is, I mean, if you look in the literature, you still have this year people publishing articles trying to understand why, okay? So it relates, obviously, to the Hofmeister series, for those of you that are chemists. It has to do with the radius and the charge of the anions, but this is still debated, okay? This is not very clear. And the Hofmeister series is actually an empirical knowledge. I mean, there is no very strong, I mean, this notion of soft and hard ions is not very clear in the literature. And as I said, there are still people publishing theoretical paper trying to explain that. But but the second, so the first message was solubility depends on salt concentration, solubility of the polymer. And second message, it depends on an anion with a series that is very similar to the Hofmeister series. Meaning that, for instance, you see sodium, the solubility is degraded much slower with hydroxide than with carbonates. Okay, but it is. Okay, so we know that the solubility of PEG is degraded when we put hydroxide in solutions, which is what we do to activate the system. And it's going to be worse with carbonate, but let's wait for that. And let's just talk about the hydroxides for the time being. So from that, what can we do? As I said, we cannot measure the Fleury parameter. What we can measure is the intrinsic viscosity of the solution. Actually, we measure the relative viscosity or the specific viscosity via a capillary viscometer. And doing that at different concentration of polymers, we can extrapolate to 0. That is, we can get the intrinsic viscosity of the polymer in solution with water. So this is an experimental measurement. So based on theory, but this is something that's measured experimentally, the intrinsic viscosity. And then again, we go back to our forefathers, Fleury, and there is a model linking the intrinsic viscosity to the size of the polymer. So here I took a typical value, which is typically, which is the one we used. And this is just orders of magnitude. So if you remember, I gave you a mass that was slightly different, but okay, but it doesn't matter. We are dealing here again with scalings, okay? And here a parameter that describes how the monomers are distributed within the blob. And if it's Gaussian, this can be calculated. And if you assume a Gaussian distribution within the blob, this gives you this value here. So some people say 3, some people say 3.5, but again, it doesn't really matter for the sake of demonstration here. What's important is that we can measure the intrinsic viscosity of our solution, whatever the composition of the solution, and we can relate it to the radius of the blobs formed by the polymer in solution, okay? So we have a very simple way, without going to neutron scattering, to actually appreciate how the radius, and this is relatively variant because this is to the cube, how the radius evolves in solution by simply measuring the intrinsic viscosity with the capillary viscometer of the solution. And what do we see? Well, we see that indeed the viscosity depends on the solvent, excuse me, and the viscosity drops when I go to, when I dissolve sodium carbonates in the water, and even more when I dissolve in sodium hydroxide. I don't have the concentration used here, it's missing, I'm sorry. But the message is that the viscosity drops, and that means that also the radius drops, meaning that the blob tends to shrink. The quality of the solvent is degraded, as I said previously, okay? So here I plotted the raw data, which is the specific viscosity with respect to the activator molality, and we see indeed the specific viscosity decreasing, and we conclude that the radius has changed. So this is what is chemicized here. I have my happy polymer in solution, okay? And then I add salts in it, and it shrinks, it shrinks, it shrinks, it shrinks. Okay, progressively. It remains in solution. It's not a phase separation. You are well before the cloud point. So if you look at your solution, it's still transparent, but the conformation has changed. And we have no direct proof of it, but the correlation is striking, or if you want, seducing. And so the story I want to tell is that as we add sodium hydroxide, progressively the coil shrinks and the steric effect is less and less pronounced, and therefore the yield stress increases. Okay, that is the interaction between the grains comes back into the story. After a certain level, of course, you have salting out, yeah, so the polymer is not soluble anymore, and then it's as if there were no soluble. Okay. So the story seems relatively simple in terms of sodium hydroxide. And the message also is very simple, is that don't just look at the solubility, just realize that the conformation of the polymer also changes before it's salted out, okay? Just because the quality of the solvent changes. Again, the values here, those are, those are just, don't take those values as face values, right? What's important is that they change, okay? We have a prefactor here that it's, okay, we took a Gaussian model, but maybe it's not fully Gaussian, the distribution of the monomers inside the core. You know, there are many different parameters in this equation that are questionable, so the value, but what's important is that the radius of the core drops by a factor of 50%, so it's not negligible. At values of concentration of activators expressed in mole of sodium oxide here that are relevant to cement activation. Okay, so now more complex case, sodium carbonate. Sodium carbonate, again, without super plasticizer, they don't change the yield stress of the suspension. But when I put the super plasticizer, again, the yield stress disappears. But when I put the sodium carbonate, boom, it comes back immediately. So we don't have this gradual effect that we had with sodium hydroxide. So something else is at play here. And this is what I had ruled out for sodium hydroxide. This is the poor adsorption that comes back into the picture here. You can see that with sodium carbonate, the amount of polymer adsorbed is much lower than without sodium carbonate. So here, something goes on. We don't really know exactly what, but something in presence of sodium carbonate prevents the polymer, or doesn't fully prevent, but reduces the ability of the polymer to adsorb on the surface. Okay, so the adsorption is lowered. Again, we have no direct proof of that, but we know that calcium and carbonate form strong ion pairing in solution, just like with sulfates. And probably this has to do, since the adsorption of the polycarboxylate ether, which is anionic at high pH, is actually mediated by the calcium that adsorbs on the surface and inverts the charge of the cement grain or the slag grain. If this calcium is mobilized by carbonates, we can understand that it won't be able to attract electrostically the carboxylate ether, our super plasticizer. It's purely speculative, okay, but it's not shocking, let's say, okay, that carbonates have this effect on adsorption, and an effect that hydroxide would not have, and that we didn't see on hydroxides. Okay, so here the situation is more complex. We have at the same time the shrinking of the polymer and a reduced adsorptions, okay? So to summarize what I just said, the quality of the solvent is something important that is schematized here, but you see that how the polymer is symmetrically shrunk on itself. So this is something that has to be taken into account to understand why and designing polymers to fluidify alkali activated paste. But this is not to say that adsorption doesn't play a role. We have seen with carbonate that also is very important, okay? But I want really to insist on the fact that this has been, in my opinion, too much overlooked in the literature. People thinking in terms only of adsorption or of solubility, salting out, soluble, not soluble. But there is this all in between where it's still soluble, but not as efficient as dispersant. Okay, a little pause. Now we go to the silicate. Silicate is another story because you see that already silicate anions are relatively good at dispersing. So the yield stress is depressed. So the issue is not that much, in that case, the issue of deflocculation, but it's more an issue of time evolution of the modulus. Here we plot the elastic modulus with time, and you see something very striking. I'm going to go very fast on this because they are models, but I don't want to go too much into that. But they are actually, you see that usually when you have stiffening of the contacts between grains, this leads to a logarithmic growth of the elastic modulus. You see that for just a suspension of slag in water, a suspension of slag in water with carbonates or with hydroxide. It's the shape of the curve remains more or less logarithmic. But you see for silicate, you can adjust as you want the curves. You will never put a logarithm in this growth here, okay? So something else, something very different is happening here. So what is the source of this steep increase? How can we understand it in terms of alkali activation, and why is it important? So I don't want to go too much into the models that have been developed by Bonacci and Xavier Chateau at École des Ponts. But this is just to say that people have developed models to explain this logarithmic growth. but this is clearly not something we observe with silicates. I don't need to go into those curves. Just this is enough, I think, to make the point. Okay? And so I don't have to go into the theory and that you could discuss right, wrong, so I don't care. But here we have something that mechanistically is obviously very different. So what is it? So we go to my old love, let's say, yeah, NMR, to identify, so this is a calorimetry, but with NMR we identify the different chemical events associated to the heat release. And what's interesting is to look at what's going on at relatively early age, you see, between the first 24 hours. And you see that the system activated with sodium silicate is very different from the others at very short time. There's already a lot of heat release. There's already a lot of chemistry going on that can be associated by NMR to the formation of what we call a Nash gel, but is basically a hydrated aluminosilicate sodium gel, okay? And this occurs relatively early, I mean much earlier than in systems that are activated with sodium carbonate or sodium hydroxides. So this is to say that here probably the growth of the elastic modulus is not associated with contact stiffening, but by volumetric fraction increase. Okay, we are precipitating continuously solids. Okay, so again, something very different. So to summarize what I said, dispersing effect, solvent quality, very important. Adsorption, of course, also. And in silicates, something is going on that is associated to the initial massive precipitation of solids. So, how can we go against those effects that are relatively troublesome in terms of the workability of the paste? Well, we have seen that with sodium hydroxide, this is an issue of solvent quality. So we need to find polymers that have a high resistance to ionic strength. So we are working on it. We have some ideas. With sodium carbonate, we see that we have an issue also of adsorption. So we need to find a polymer that has a good resistance to ionic strength, but also a strong affinity for the slag surface. With sodium silicate, the issue is different. We see that our problem with workability with sodium silicate is that the reaction somehow proceeds too fast. So we need to slow it down, okay? So this is just a summary to show you how those studies of the behavior of the system really at the molecule and the molecule scale can guide the industries, and in particular that was funded by CRISO, to design new polymers. So I'm not going to give you the recipe for those polymers, but just to show you how our understanding of the physics of the thing in solution and of its chemistry can help design new solutions. And I will, because I cannot talk too much about the formulation of the polymers, I will spend more time on the sodium silicate, which is not a polymer issue, but how can we retard this what is deemed as too fast evolution of the elastic modulus. So this is the second part of my talk, but in order to do that, we need to understand the alkali activation. If we want to slow it down, we need to understand it. So what is it? So you have all seen this type of schemes. Basically, if you start with sodium aluminate, silica aluminate. So here I switch to thermally activated clay, but the general trends are the same with slag. You have a dissolution, polycondensation, and repolymerization. So I just want to say a very simple fact is that the dissolution is activated by the alkali ions. That's why we needed in our activators. That's why they were alkali, the activators actually, because the siloxane or the SiOAl bond are attacked by the hydroxide in solutions. But once the silicate and the aluminate ions are released in solution, they recondense to form the solid, being a glass, a hydrated glass, a gel, or a so-called geopolymer, an ash or a geopolymer, but this condensation releases the hydroxide ions. So in a sense, this is catalyzed by the hydroxides. Okay, the water here is not really a reactant. It's just a source of OH minus to dissolve the system and allow further precipitation, of course, of the aluminates and of the silicates. Okay? So let's see what we can understand about this first process of dissolution and recondensation. And in particular, why do we need to do that with silicates? Because if you look at my scheme here, you would say, okay, I just need sodium hydroxide. But we have seen that it's very different with silicates. So what makes the presence of the silicate make this scheme different? So to do that, we just follow the system by NMR, doing aluminum-27 NMR in the liquid phase. So we are going to look at the aluminum in the liquid, not in the solid. And we look at the intensity of the signal that we calibrate somewhat artificially in terms of aluminum in solutions. We say as the aluminum-27 NMR signal goes up, that means there is more and more aluminum. So this is true up to a certain level, and then life becomes more complicated for reasons I will try to explain briefly. But at the beginning, when you had just dissolution, you just release aluminate ions to the solution, and the signal is more or less quantitative. Okay, so once they start to polycondensate, life becomes more complicated. But at the beginning, when the system is dominated by the dissolution, we really have a reading here of how much aluminum goes into solution. Okay, so if we do that with different amount of calcined clay, metacaolinite here, so we have different curves. Obviously, the more we put metacaolinite, the more surface we have, so the more dissolution there is. But if we cross that with calorimetry, so we measure at the same time scale, we measure the heat released, varying the amount of calcined clay in the activating solution. We can plot one versus the other. So we evacuate the time variable. So we evacuate the kinetics in a sense, okay? And we just have how much heat is released per aluminum dissolved in solution. So we have the heat of dissolution, and you see that all my curves that were measured at different metacaolinite concentration actually collapse onto a master curve, because yes, the kinetics was not the same because the surface area was not the same, but the mechanism, the chemistry is the same, so they collapse on the same curve at the beginning. There it's a little more complicated, but they collapse on the same curve here. And so my point here is to say that the inverse of this curve here is the enthalpy of dissolution, expressed by moles of aluminum. Okay, so if I do the same thing, varying the alkalinity, the amount of sodium hydroxide, different curves, different isothermal calorimetry, and same thing, master curve at the beginning. So whatever the concentration of sodium, the chemistry is the same. What changes here is how far does the reaction go. And this is normal because the more hydroxide I have, the more I can dissolve my metacaolinite. Okay? So this is not a big surprise. This is more a check of what we are doing is meaningful. Okay, we recover something that was very expected, is that the hydroxide concentration actually changes the completion of the reaction. So it changes the moment where we switch from pure dissolution to dissolution plus polycondensation, but the initial dissolution mechanism is always the same. So the beginning is very clear. We have hydroxide in solution. They attack the clay. They release the monomers in solutions. Okay. Where it gets more interesting is to understand the role of the silicates. Now I keep the amount of metacaolinite constant, I keep the alkalinity constant, and I just change the modulus by varying the concentration of silicate ions, by dissolving more or less silica in the sodium hydroxide, basically. So again, at the beginning, pure dissolution. But you see what's interesting is that if you have no silicon, no silicate ions, you dissolve your metacarolinite, and that's it. And when you put more silicate, you see that you change the behavior of the system. You go to a higher level. The alkalinity is the same. Okay, you have the same amount of hydroxide in solution at the beginning. But still, this has the fact that there are silicates impact the chemistry in terms of the polycondensation and how far the dissolution goes before polycondensation starts to really dominate the system, i.e. the geopolymerization or the formation of the Nash gel, okay? And the idea is that, do you remember my silicates? I mean, you don't remember because I didn't say it, but the silicate ions in solution, they bear hydroxides. And that's the drawing I showed at the beginning, is that when those ions polycondense, they release an hydroxide, okay? So those silicate ions that I've added in solutions act actually as an hydroxide reservoir that replenishes the hydroxide in the system. So that's why actually if you want to do a geopolymer, or if you want to carry your reaction far enough, you need the silicate ions initially in the mix, okay? Because if you just put sodium hydroxide, you're going to use all your alkalinity, the pH will drop, and the reaction will stop, okay? So I think with that, with this very simple experiment of crossing NMR measurements and heat release, we got something relatively interesting here, which is the role of the silicates to direct the system towards more advanced dissolution of the clay. So this is what is summarized here, is that we have introduced a loop in the system here with a reservoir of hydroxide that come and nurture the dissolution of the clay. Okay, now, so I'm going to go very fast here because I think this is interesting. Not published, huh? But so we understood this more or less, this idea of the role of the silicates. But what about what is going on here actually? What was responsible for this increase of the elastic modulus? So I skip this part. Just ask you to believe me on face value or come to me. I'm here until Friday evening. Yeah? So if you want to discuss those experiments, I'm more than happy to do it. But by doing different measurements, always in the liquid state, but with different pulse power in the NMR experiment, we can recover the amount of aluminum in solution at a given time and the amount of aluminum in the Nash gel or the geopolymer. You choose your wording, I don't care, okay? And you see that it's relatively linear. So that's after a certain moment, you come to completion, it doesn't, but this is relatively linear. So this is interesting because this is not at all what we see, for instance, when we hydrate halite, where we have this sigmoidal behavior. Here we have a really linear behavior. The problem is that at a very short time, there's still a lot of metacarolinite in the system. It does, and for reasons that I don't have time to explain, the measurements are not accurate at very short time. So we have to resort to another measurement. Again, I go fast, which is relaxometry, where we follow the transverse relaxation time of the molecules of water adsorbed on the surface, of water in the paste, as a function of time, and as a function of time, and as a function of frequency. That is the NMR measurement frequency. Why do we do that? Because relaxation of your proton in water is actually a sum of two phenomena. One that occurs in the bulk, due to the fast reorientation of the molecule of water. And because this reorientation is very fast at the NMR time scale, this is, with the frequency we are probing by NMR, frequency independent. But when the molecule of water is adsorbed on the surface, its motion is constrained by a 2D diffusive path on the surface, and it becomes frequency dependent. So we have actually here, through the analysis of this frequency dispersion of the relaxation rate, we gain information on the diffusive path on the surface with characteristic times associated to this process. But I won't tell you the whole story because I don't have time. But if you go at very high frequency, you're probing very short time. Okay, so the molecule of water doesn't have time to absorb on the surface. So you just have the relaxation of water in the bulk. Very small frequency, you're probing long time. So the molecule has time to come to the surface, and it has time to probe the whole surface before it desorbs. It's a little more complicated than that, but roughly speaking, that's what it is. So at low frequency here, asymptotically going to zero frequency, you recover the surface area of the system. So that's what I have written here, the full expression. But the asymptote here at zero frequency is, of course, frequency independent. And what's important is that you have time here, characteristic time that describe the interaction of the molecule of water with the surface, but you have a prefactor that corresponds to relaxivity and is proportional to the surface area. So we don't know the proportionality constant here, but what we are measuring here is proportional to surface area. So we can follow development of surface area with time at relatively short time. Well, we need time to prepare, put in the relaxometer and blah, blah, blah. But you see, like, even during the first hour, we still have this linear development of surface area. So the whole mechanism is linear. With those two NMR together, with the second method, we are able to bridge this little gap here. And everything looks like as if the process of the Nash gel formation is constant with time. So it's very different with the cement paste. No induction period. We have a linear process, which, again, I can discuss with you, but that translate actually the fact that we are not in a nucleation and growth process. It's normal. We are dealing with a Nash, with a gel, with something amorphous, so there is nothing to nucleate. And we are dealing with a salt-gel separation. And this salt-gel separation occurs because we are dealing with a high concentration of silicate initially, okay? So we are past the inflection point of the free energy curve. And so we go from nucleation and growth, zeolite formation, to spinodal, to make things look smart. We can say spinodal, but basically a salt-gel separation. Okay, that is, there is no energy barrier to the phase separation. It proceeds right from the start and in the volume. So in my opinion, this is the fundamental difference between those behaviors here. Okay, here, as I said, contact stiffening, and then at some point you will have nucleation and so on. But here we have immediately from the start this phase separation that has no barrier, and that just as in a salt-gel reaction, and proceeds continuously. And this is because I already have silicates in solution. So you see the two studies come together here, and we are dealing with very different phenomena at the molecular scale, but that translates to very different macro scale properties, which is a time evolution of the elastic modulus. Okay? So, okay, he has an explanation, you believe me or not, but then so what? But so what is that now we understand that what we have to control is this phenomena associated with a high initial silicate concentration. So if we add a retarder, for instance, zinc nitrate, this zinc nitrate has to mobilize the silica initially to prevent this salt-gel phase separation. And in our opinion, this is why zinc nitrate, here expressed as zinc oxide content, but zinc nitrate is such a good retarder. And if you look at the evolution of the elastic modulus with time, you see, with silicate activation, this very steep increase, and so this is very preliminary result from the thesis of Alice that started less than a year ago. So, and with zinc, we recover this pseudo-logarithmic behavior. So there's an indication that the chemical mechanism, the phase separation mechanism, is switching here. And actually, this can be related to this. What we have observed is that I have my alkali sodium silicate solution. I put zinc nitrate in it. I precipitate something. And this precipitate, I don't have the data here, but contains zinc and silica. So it's amorphous, so we still have to analyze exactly what it is, but this is mobilizing part of the silicon, and a large part, 20% of the silicate concentration initially in solution, in form of a solid, okay? And then it's as a solid, so we don't have this gel formation because we have depressed the silicate concentration. But this gel here is metastable, and it redissolves after a while, and the reaction proceeds again. Wow. So this is, as I said, this is kind of confusing, going in a lot of different directions. But this is often what occurs when we try to link things at different scales. We still have a few years to work on this. We still have funding for a few years, so we will look more carefully what is the chemical nature of those precipitates. Can we relate by ICP, for instance, the silicon and zinc concentration in solution with the time evolution of the rheological properties, and of course the heat development here, I mean the reactivity, okay? But our intuition is that everything is linked to this idea of how much silicate I have in solution initially when the reaction starts, and how the system phase separates. Is it waiting for nucleation and growth, or is it immediately proceeding into a precipitation and amorphous gel? Okay? And so in our opinion, the way to control this is by engaging temporarily the silicate, and certainly not by seeding or things like that, because there is nothing to seed here, because there is nothing to nucleate. So it's very different from the ordinary Portland cement case. I'm sorry I was too long. So I will go short on this, but of course what I talked today is not my work, it's the work of younger people who did all the job. Nicolas, who's working with me in the lab, Clara, who had a baby last week, actually, bravo Clara, working now at Saint-Gobain Recherche, and Alice, but both were funded during the PhD by CRISO. So I need to thank all the people at CRISO, because they were very active in the scientific discussions, and they not just fund providers. And of course, for everything relating to NMR relaxation, this has to do with Pierre Levitz and Anne-Laure Rollet at Phoenix. Sorry, I got carried away. Yeah.
Thanks, Jean-Baptiste. It's perfect on time, so it's okay.
No, it's too long.
No, it's perfect on time. It's 1 hour. So I don't know if you have any question for Jean-Baptiste on the seminar just gave? No? Yeah. Nicolas?
Please, no rheology, please.
Please, no rheology.
Well, thank you, Jean-Baptiste. It was, I'm happy to know what you're working on these days. It's very, very interesting. On slide 33, you use the Flory theory
okay.
to measure the diameter or the hydrodynamic radius.
The variation in diameter.
Yes. But there are a few things here that are, I don't know, knowing you, I'm sure you pay attention, but as I'm very interested by this type of technique, I want to check that you have the same vision as I do, which is, did you take into account that your solvent viscosity was changing because of the ionic concentration?
No. Because
for this type, well, you had this thesis. I was a member of the jury some years ago when you had alkalis to distill water.
With respect to the rheological behavior, or with respect to the polymer
33,
conformation?
the viscosity, the capillary viscosity of the solutions. Yeah. On 33, not 24. Yes, this one, yes. So, because, you know, the intrinsic viscosity here is computed from the viscosity that you measure, and then you have to relate it to the viscosity of the solvent. And here, adding
of course, yes, this is by comparison with.
All right, so this is
a time drop. I mean, you know the measurement, right?
Yeah. So it is accounted for, right?
The solvent?
The
Pure
solvent viscosity changing because of the ions.
Yes, yes.
Yeah, okay,
That
okay,
was
okay.
your question. I'm
Yes, yes,
sorry.
yes, yes,
I
yes.
thought it
No,
was in
because
terms of the conformation
I have
of the
seen in
polymer.
literature people using this to measure size
no.
of polymers and then
No,
not
no.
correcting by the change in
No, the T0 is taken with the salt, the ion.
Okay, so you divide by this reference. Okay.
Yes, yes, yes.
And then my second question is that what you call viscometric radius here, what is exactly? It's really the size of the overall molecule, including the backbone and the side chain. But in fact, you are discussing the fact that only the side chain is changing size and shrinking. No, backbone too.
Yes, but I don't.
But they don't have the same fluoriparameter.
Ha. Okay, good point. This model is for a polymer.
Is for
homopolymer. I mean, this is a
this is the basic
original model is for homopolymer.
Okay.
And this is modified for copolymers.
Copolymer in the flexible backbone.
Okay. The fluoriparameter is assumed not to be that different between the polymethacrylate and the polyethylene oxide. But you're right. It's
yeah, but the thing is that viscosity will be influenced by the space that this worm is occupying.
Exactly.
Whereas what you are interested in is the space that one elementary pearl, if I take your pearl collar,
so
pearl necklace.
You're right. What's missing from this drawing is that you have the hydrodynamic radius
of the overall
that
structure.
may relate to the viscosity. I don't know. I'm not a specialist, but. And there are scaling laws relating the hydrodynamic radius to the blob radius and to the chain length, of course. Yes. Okay, so that was not your question. But,
it is. The thing is that for this type of complex molecular structure, it's always difficult to relate a size to a viscosity. That's
yeah.
But you see a decrease, but then you don't know if it's the decrease of the entire worm or the decrease of the side chains that will of course contribute to a decrease of the worm, but your drawing is very clear.
So the general idea is to say that the hydrodynamic radius relates to the blob radius.
And from a scaling point of view, it's true.
And measure the hydrodynamic ratio. I mean, I measure a radius that is probably linked to the hydrodynamic radius by viscosimetry.
Yeah.
And the theory for homopolymers says that the hydrodynamic radius relates to the blob radius.
Yeah.
So if my blob shrinks, the overall radius shrinks also. But you are absolutely right that there is no reason for the fluoriparameter to be exactly the same
for the two components.
And it's actually even trickier than that because the monomers, the interaction between the polyethylene oxide monomers and the metacrylate is not the same. I mean,
and
so
then you said
the limit,
you said that you did not measure it, that it's an indirect proof, but for this type of monomass, you can use dynamic-like scattering. And once again, you will measure an overall radius, hydrodynamic radius of the coils.
We tried, but it's not so.
No, it's not working that bad. And I mean, you won't know.
We had a large error by DLS. So I'm not sure we could distinguish differences like that by DLS. On those polymers that don't contrast, I mean, the index is not that different from the one of water. So the scattering is not.
Well, you know the work of Ella.
Yeah, I know.
And then for PCs, she was able to really detect some molecular mass variations that were not, or molecular structure variations that were not really big, because plus or minus 1 nanometer on DLS in this range is a lot. But.
Okay.
I mean,
in my opinion, you have to go to neutron scattering if you want to have real.
Yeah, of course, but that's a bit rarer.
And then you say, oh, but you change your solvent with heavy water. And
yeah, for sure. Yeah. Okay, thank you again, Jean-Baptiste.
Thank you. Any other question in the room? Just to clarify. I don't know if you mentioned, but for sure your mixtures that you were testing with the different activators were totally stable. They were not suffering any chemical change. Okay, in this, I think it was already.
We are looking at short times. We are looking
Yeah,
at,
that's it.
yeah.
But I'm totally agree.
And we check by chromatography.
Yeah, I think that is
course.
a good point. So they are stable and you get one parameter out of the system. So, but you mentioned there is some work talking about this competitive adsorption, mainly with sodium hydroxide. We observe here the same. We don't change adsorption. Okay, when you have sodium hydroxide and you have water. Okay. Yeah, we have the same.
So if Marta agrees,
no, with sodium silicate is different. Okay, we really see. But any idea what is from where is coming these different results? You don't.
Why people claim competitive adsorption with hydroxide? I don't know. I don't understand. I don't understand how you can even imagine a competitive adsorption with an hydroxide. Mm-hmm. It's as if saying there is a competitive absorption with water. It's absurd. I don't understand.
And now, just with respect to the last part, when you are talking about controlling rheology, when you use sodium silicate, you are using a retarder. Is that enough to have the rheology you are looking for? Do you think?
No.
You don't?
No, I know, no. It's not, it's more opening the window of workability that controlling really the fluidity and the yield stress.
Yeah.
So you need to, you cannot do without admixture, but we still
you
don't
have
have
to work
them.
on,
Yeah.
Okay.
Organic admixture.
Nicola?
Probably when you delay the silicate effect, then admixtures can start to work again in this type of system, right? Have you tried, when you delay the system, to try the effect of PCs?
Yes, I don't have the data here, so I invite you to come on October
in November. Yes.
November 21st. I know you're an impatient man, but I don't remember the
because
data,
you're speaking.
It was a mess. It was going in every direction. We had a lot of problems putting things in order, so we decided to focus first on understanding the chemistry of zinc in those systems.
Yes.
And then we'll put the polymers. But we, of course, at the beginning, we just mix everything and look what happens. And it was going in all different directions.
Yeah.
So
because you speak of a volumetric increase at one point. Another way to say about the same thing, but a different word in real physics, is to say that you create a viscoelastic gel between the grain. And viscoelastic gels, of course, they're not as rigid as the grain themselves.
Okay.
But then they create these viscoelastic forces that are. We worked a bit together on that during the PhD of Aurélie Favier.
Zinc?
No, not zinc, but the viscoelastic gel.
Oh yeah. Cool. You lectured me on that, and I think I got some understanding thanks to you.
So I think
about stress concentration between grains.
Yes, exactly. Yes. Yeah. Thanks.
Thank you. So I think it's fine. I think we already reached more or less the time of the end of the seminar. Thank you very much.
Well, I want to thank you all for your attention, and again, feel free to discuss. I mean, I'm here for that.
He's going to be here, it's true, until Friday afternoon.
Yeah.
So tomorrow is going to be complicated because we have different meetings, but Friday is possible. He's going to be in the chemistry of cement group, Química de Cemento. So if you want to talk to him, perfect. And pleasure always having you.
Yeah.
Thank you to all of you. And let me, I didn't say goodbye yet to you, but let me move into Spanish because I'm going to show the next seminars and then I will say goodbye. So just a bit of advertisement. Where is it? Here. For the next seminars, you know that I said we were going to organize lo estoy diciendo en inglés, en español. Os dije que queríamos organizar los jueves, el primer jueves de cada mes, un seminario para seguir un orden. Bueno, pues no lo estoy consiguiendo. Los siguientes dos seminarios son en diferentes fechas, pero creo que son los dos muy interesantes, ¿vale? Primero va a ser el siguiente va a ser el 16 de octubre. Veis que son unos colaboradores de nuestra compañera Gloria Pérez Y bueno, pues nos van a hablar de investigación aplicada al apoyo de políticas públicas para mitigar el calor urbano. Hay un estudio, un caso estudio en Brasil, y son las profesoras Claudia Cotrín Pezzuto y Lía Toledo Moreira Mota. Ese es el primero, nos lo apuntamos. Y el siguiente va a ser el 20 de noviembre, ¿vale? He conseguido que sea un jueves, pero no el primer jueves del mes, problemas de agenda, ¿vale? Que es en torno a la ingeniería para el futuro de la construcción, innovaciones y resiliencia, sostenibilidad y diseño. Y tenemos 3 ponentes, David Zampini, Igor de la Varga de CEMEX y Roberto Starr, que no he puesto la afiliación, que viene de México. Bueno, nos lo apuntamos, ¿vale? Para la siguiente, os iré haciendo recordatorios, ya sabéis cómo soy. Y, okay, and now yes, I say goodbye and hope to see you in another seminar again in the future, and you update us with your results, okay? Big thank you. And to all of you for attending, okay? Gracias. I prefer to do it in